This afternoon I briefly wanted to show an example of an application of MD to a real-world problem. And this real-world problem is I found, strange process called magnetic pulse welding. Those who ever had to do with different types of welding, there's a huge number. We spoke this morning about friction stir welding, another process where one does not believe that it works, but apparently it does. And this magnetic pulse welding is, as I said, similarly surprising. It's a special type of collision welding. Collision welding, I think the Russians invented. You just hit two pieces with high speed, and if the parameters are properly chosen, they form a connection. Yeah? But this explosion welding is hard to control. That's why they developed other tools to accelerate one part of the welding seam towards the other one. And this is done in this magnetic pulse welding. And here I wanted to show first some experimental results and then some attempts to model it using MD. So here you see the principle. You have a coil, magnetic coil with an iron core. Below this core you have half of the parts or one of the parts you want to join. The other one is at the bottom here. This one is called the flyer and the other one is called the target. Nice terms. So, and what you do is through this coil you have a huge battery of capacitors. Through this coil you discharge these capacitors. So you have a huge current flowing through this coil, which means a very short and intense magnetic field. This magnetic field then induces eddy currents here in the flyer. And as you probably know, these eddy currents or the magnetic field, the eddy currents is against the incoming, the direction is against the incoming field. So you have a repulsing field here between the iron core and the flyer, which means that the flyer is accelerated downwards and hits this, this target here. It's really applied for special applications, I think. One application is to join tubes. Yeah? So you have two tubes, and then you, not this geometry, you put a circular coil around it, and then you can, with one shot, join these two tubes, and you get very good connections there. And the parameters you can vary here is the pulse energy. It's typically given in kilojoule. In principle, a further parameter, and this will be seen in the next slides, is the velocity of the flyer. But this you cannot control, it's given by the pulse energy. But then you can adjust the distance here. And this distance, as you can easily imagine, decides how they hit each other. And this then translates in a collision angle. So initially they fly like this, but it's slightly inclined. And then you have a elastic deformation or plastic deformation moving through this material. It's shown here. So here you see a kind of cartoon of this process. That's the flyer which first joins here, and then you have this migrating interface, and depending on the distance here you adjust the angle. And it was shown just by experience that there is a critical velocity and a critical angle, and we tried to understand it. Here you see a real example, cross-section. This is aluminum and copper. So the upper part is aluminum. It's well suited for aluminum because of the high conductivity of aluminum. I think it's not that well suited for steel, but I'm not 100% sure. And there are many details about the microstructure of this interface, which I will show here. So what people claim just by experience without knowing why it is so, that if the interface after the process shows such a wavy appearance, then it's probable that you have a good joint. If you don't find it with planar, typically the joint is not good. And what we study was, or one point we wanted to find out what really leads to the joining. No? So you have this wavy appearance here, and the amplitude, and I think also the distance depends on the energy here. And then the question we were interested in, I think that's visible here in this close-up, do we find at first intermetallic phases which form here in this joint? This comes a bit from our experience with friction stir welding. There we always found intermetallic phases. And the second question is, does the collision energy lead to instantaneous melting of one of the constituents? As we will see, it's not out of question. We found further things here. Here are SEM pictures. I don't know whether you have experience with SEM. With EBSD, electron backscattering diffraction, you can easily create nice colorful pictures. There's this acronym CFD, computational fluid dynamics, which is often translated colors for directors or colors for dollars or so. It's a bit similar here. So perhaps we should try to find another translation for this EBSD. But nevertheless, it allows you to tell you something about the microstructure, about the processes which took place here. Here in the upper part, which is the aluminum part, you see extremely fine-grained material. Somehow I lost, oops, sorry. Somehow I lost the scale bar here. Is there a scale bar? Here's one, and this one is a close-up. I think it's sub-micrometer size, these grains here. While here you see it's coarse-grained, but you see here an extreme deformation of the grains. So apparently there's a shear deformation on the copper side and some process taking place in the aluminum side, I would say. Here in this region you even find smaller grains here. All these pictures, they are used different types of evaluation of the EBSD data. You know EBSD? It's, as the name says, electron backscattering diffraction, so it allows first hand to determine the orientation of the different grains. So the colors just gives the orientation of one grain. Here so you see this color code here. So red is 001 and so on. But then you can do other evaluations. It's BC, that stands for band contrast, which basically tells you how strongly deformed your region is. Now this band contrast is an indicator how many dislocations or so you have in a certain region. So for example here you see a very poor band contrast, it's black, so there is the machine does not manage to index the diffraction patterns and so on. Okay, I think I said something wrong here. I forgot to mention this part of my presentation is from a student, David Stein, and he claims that this part here is recrystallized copper, not aluminum. So the aluminum is only up here. Here you see better the interface between aluminum and copper. And then we looked closer into these, these regions in the wake of the waves. I think it was probably this region here, this one here. So what you find here is are regions which look like dendrites. So this might be an indication that there's a short-term melting of this structure, which would nicely explain why you get this good joining here. And something I found astonishing, you find all types of different intermetallic phases here in this region. Here is a phase diagram of aluminum copper, and for different points where we took EDX spectra, you find different compositions, so this indicates that these are some intermetallic phases. But the more astonishing thing I found, I told you already that we are interested in these GP zones, and in these regions where you still have some aluminum, there is a high amount of copper dissolved. If it melts, that's not surprising. But then if it resolidifies, you quench in a huge amount of vacancies. And as I told, excess vacancies are responsible for the formation of these precipitates. But instead of forming these normal GP zones, you find mostly, I'm looking whether here this is a GP zone. This is an atomic resolution image here. This is a single plane here of copper inside the aluminum matrix. But much more, you find here these double layers, so that's the GP2 zone. And they are not expected after such short times. Yeah? Furthermore, you find quadruple here or triple plates here. And I recently had to review a paper where the person claimed that he found a new phase in the aluminum copper phase. He called it GP3 and was extremely proud. But I think that's not so unusual. So these are GP3 and GP4, if you like, if you want to make some noise. More interesting are these ones here. These are theta prime phases. I'm not sure how familiar you are with all these metastable phases in aluminum copper. You start with the aluminum copper phase, with the GP zones, GP1, GP2, and then at elevated temperature you form this theta prime, which is a major hardening phase in aluminum copper if you do artificial aging. Then there is finally the stable phase, again with this stoichiometry aluminum 2 copper, the theta phase. But it forms mostly on grain boundaries and is not helpful for hardening the material. So if you want to have a peak hardened material, you go to high density of theta prime. And you find microscopic theta prime phases here. Normally they are much smaller, much larger, sorry, and also have a larger extension. Yeah? So they are nearly as wide as long here, or maybe 1.5 or so. This would more correspond to what you showed for the interface anisotropy, and this, what you typically find, this very long extension of the theta prime is, in my opinion, controlled by kinetics, that the adhesion probability is higher on the edges here as it is on the faces. Here this seems to be not the case. So you are highly out of equilibrium, and we're now trying to simulate or to reproduce this behavior by using well-controlled quenching conditions. Perhaps you know melt spinning is one of the processes. So you take aluminum copper alloys, you have the melt, spill it onto a rotating wheel, so you get a very fast solidification, and then we can try to find whether we also get such strange microstructures. So at this point we came to the conclusion that there is probably a melting of at least part of this interface zone, which is also plausible if you just consider the energy involved here. You have pretty high velocities, 500 meter per second, up to 1,000 meter per second of the aluminum atoms. So if they hit each other, they just dissipate this kinetic energy as heat, and this leads to probably to a melting. Oh yeah, here are some close-ups for those who don't believe it. So that's the GP1 zone, that's the GP2 zone, that's the yeah, if you like, GP4 zone. By the way, they always have 3 aluminum interlayers. Yeah? So you have 1 copper layer, then you have 3 aluminum interlayers, and then you have the next copper plane. Here, similar, you have 3 aluminum plane, the next copper layer, 3 aluminum plane, next copper layer, and so on. Don't ask. I just wanted to say, don't ask me why they are shifted. So, I don't know. Perhaps due to the shear, but I have no idea. Okay, and this was a point where we tried to set up a molecular dynamic simulation. Why does it sound feasible? If you consider the collision speed, 500 meters per second, if you translate it in our simulation units, it's 500 nanometer per nanosecond, or 500 picometer per picosecond. 500 picometer, I think, is 5 angstrom. So in a picosecond, you move already a few angstrom. So if you do a simulation of these bars here, I forgot, had thickness of maybe 10 nanometers or so. So you can cover an elastic wave migrating from, or not only an elastic wave, a wave migrating from this collision region to the outer part here. This was another student, Benedict Eklesivas, who did these MD simulations. At the end, I will also show the shortcomings of these simulations. They are not all too serious or so. Yeah? But we tried to reproduce as far as possible the geometry. We have 2 pieces here, the copper and the aluminum, which hit under an angle alpha. And then he decided to measure the local temperature and the local pressure in small parts here. He made a mistake, which turned out at the very end, when he already, I don't know whether he already submitted the thesis or part of the, or right before, which I mentioned here. What he did was to attribute relative velocities of the aluminum and the copper part here. But since copper is much heavier than aluminum, the center of mass is not at rest. I mean, this can be compensated, but this means the values he gives for the velocities are roughly by a factor of 2 too big. Yeah, so I just, in most of the slides, I divided the velocities by 2, yeah, so it's very rough estimate. Yeah, most of these procedures we already learned. How to measure the local temperature, takes the average velocity here in this small volume. Pressure, you take the virial, and then, very important, check the microstructure, and if this exists in the melt. So the first set of results, he had a kind of strange labeling of his samples or his runs. These 4 digits here stand, the first one, I think, for the collision velocity. So if there is a 1, this means, in his opinion, 1,000 meter per second, but which corresponds to 500 meter per second. Then the second digit is for the collision angle, 10 degrees, 20 degrees, and so on. Then, in the beginning, he started with cold samples, at 0 Kelvin, which probably, again, is not such a good idea. Then he changed to 300 Kelvin. These are these underscore T. And then he also did runs with a varying distance here between the two samples. That's the third digit here. So what you see here is that and I think the curves are all, I'm not sure, no. They are not displaced against each other, but because if you vary the angle, if you make a very small angle, the tip of this joint region moves faster as if you have a large angle. It's just geometry effect. I don't know, sine theta or cosine theta or something. That's why these curves are shifted. And then you get a very sudden increase in temperature here on the aluminum side, less pronounced on the copper side. The dashed line is for the preheated sample. The solid line is for the initially cold sample.
So these are NBE simulations?
I think so. Otherwise, I mean, it makes no sense.
Remove all the temperature.
Right. I mean, that's one of the complications. I come to this at the end. I mean, I think I mentioned it already in one or other of the lectures here. What happens in a metal if you have such a high energy collision? Yeah? Heat is dissipated, but how is heat transported in a solid? Only to a smaller fraction by phonons, by lattice vibration, and to a larger fraction by electrons. And of course, in any MD simulations, there are no electrons involved. So that's one of the shortcomings. So the heat dissipation is not that realistic, I would say. But nevertheless, you see this steep rise in temperature here, which gets a bit weaker if you increase the angle here. I think that's at the beginning of this collision zone, so somewhere here, and that's in the center of the collision zone. And you see that here this effect is already less pronounced. Unfortunately, I have no movies because I took these pictures just from the thesis. Here are 3 different time instants. So at 10 picoseconds, you see the joining starts and then migrates here along this line, and at the end you have this nice joint. Now we can apply all what we showed you before. You can do this common neighbor analysis, so which indicates type of phase found in certain regions. Green is FCC, red is HCP. And astonishingly, I hope it's not inverted, you find a lot of stacking faults in the aluminum part here. So these are probably partial dislocations. So I'm wondering what was this was not preheated and preheated here under different angles. This is 10 degrees, 20 degrees, 30 degrees, and so on. After some time here. And what you see here, already here, is such a gray region which could not be indexed by the CNA analysis. Which means apparently there is no reasonable crystal structure in this part, and which we could take as an indication that there was some melting during this short time here. Of course, again, one has to be very careful. What do I call melting and what do I call temperature? Tomorrow I wanted to say a few words about radiation damage. I did not want to show MD simulations, but only Monte Carlo. But there was a huge amount of molecular dynamic simulation of radiation damage. What is radiation damage? You shoot a high energy particle on a sample, heavy ion, an electron or whatever. If it is a heavy ion, you create what is called a collision cascade. So one atom, the primary knock-on atom, is hit by this ion. This primary knock-on hits other atoms, and then you have a cascade. It's called a collision cascade, which then leads to a strongly perturbed region of, I don't know the precise size, but pretty large. You can see it in the electron microscope. And what people claimed from MD simulations was that this was a molten region. And I think we discussed it one day when we went to the cafeteria or so, that molten would mean that you have a Maxwell distribution of velocities. Yeah? And I must admit, we also did not check it here. So the velocity distribution, a melt, is a thermodynamic state. Yeah? If we attribute a temperature to such a state, the atoms must obey, the velocity distribution of the atoms must obey the Maxwell-Boltzmann velocity distribution. And this was questionable in these MD simulations of collision cascades, and it's also a bit questionable if we call it here amorphous. So here you see also in copper, you see this high density of stacking faults, and I guess it's only because partial dislocations nucleate somewhere and they migrate outwards. Same here. But here, at least you get highly perturbed regions in the aluminum side. Here, this is at a higher velocity, nominally 2,000 meters per second in the thesis. Here I call it 1,000 meters per second. Here you see different time steps, 0 picoseconds, 10 picoseconds, and so on. And what you see here, you form a join, but then you have a spring-back effect. Yeah? There's so much elastic energy stored in the material that it pulls apart the two parts here. You see here this debris, or here. So you don't get a reasonable joint. Yeah? I don't know what this was. This was other parameters again, where you see a very large, I would call it not indexed zone here in the interface. So strong perturbation of the crystalline lattice. Now comes the next question. You hit these two parts, you heat it up to an elevated temperature, but what does it mean if you reach like 700 under these conditions? So what he did was also to measure the pressure. And you can use, sorry, this is in German, the second invariant of the stress tensor. You find here very high values in small regions. This is at, I would call it 500 meters per second, 90 picoseconds after the collision. Here that's 1,000 meters per second, 40 seconds after the collision. And you find pressures here, if it don't take only the red regions, but the green ones, pressures of about 10 gigapascal. Very short, but sufficient. What does it mean if you raise the pressure to such high values? You increase the melting point. I think in most materials, by increasing the pressure, the melting point increases. Ice is a counterexample. By increasing the pressure, you decrease the melting point. But water has so many anomalies. So that's. But I think in silicon also such an example. I think the melt has a lower density than the solid. I'm not 100% sure. So one has to think about the pressure here. And then here, I can draw your attention to this part here. This is perhaps what people call a jet. There's a lot of just claims about this process. So what people from this community tell you is we get a good joint if you observe this jet. What is this jet? Nobody knows. But there's a short flash forming during this collision process. And there are different possibilities what might happen. But at least here's some material thrown out. If you do such an experiment under air, this would readily oxidize and you would see this flash. Strangely, people did it also under vacuum. They still observed this flash. So here it's a better example of such a jet. Sorry, I just copied the headline here. So here you see the formation of this jet. Here you also see some intermixing of the aluminum into copper here. Sorry, I did not know. We could look it up here, what the parameters of this run were. Probably it's 1,000 meters per second and again 30 degrees or so. So I want to summarize these things. On the left side, we see an experimental graph, what the people from this collision welding community always show. It's a kind of, I wouldn't call it a phase diagram, a diagram for the good set of parameters. One parameter here is the collision point velocity, and don't confuse this with the collision velocity. The collision point moves much faster if the angle is smaller. Just a question of geometry. So like a scissors, which you close, the tip of the scissors is moving much faster than your fingers. So that's the collision point velocity, which includes this angle, and the collision angle. And what they find is here jetting and no jetting under this set of parameters. So if the velocity is too small or the angle becomes again too small, then you get no jetting. Here you find this pronounced jetting. And they also attribute this to good joints. So if you are in this set of parameters here, then you get good joints. If you are out of this set of parameters, you get poor joints. And that's what he also inspected here. So he determined whether he finds such a jet or no jet. These are the blue points versus the red points. And then lösen means loosen. It's loosening under this set of parameters, so low velocity, high velocity, low angle, and joint which remains at least during these few picoseconds or tens or hundreds picoseconds. Here you get a good joint. And what these people claim is that these lines here, that they correspond to line of constant energy. That's this graph here. So you need a kind of minimum energy to form a reasonable joint. So here, that's this, perhaps I should have shown it before. He also tried to measure the melting point of aluminum at these high pressures, melting point at 10 gigapascal. And it's just the method Guru explained. You take a molten region in a solid region, crystalline region, and then you let it run for some time. So that's the initial state, and here you see the molten region at 1200 something. It grows. No, that's strange. Must be other way around. That's a crystalline region here. So that's the crystalline region grows and the molten region decreases. And then if you go, he did not make it too fine, 1300 Kelvin, it goes in the other direction, so the molten region increases here. I think that's one of the parameters you obtain from this analysis in OVID. And so that's summarized here and compared to literature. Here at 0 gigapascal, melting point is a bit too low for this potential. Here 750, it's like 500 Celsius or so. It's more like 660 or so. So that's not very well met. Here's a melting point of pure copper. It's not too bad. It's slightly above 1000 Celsius, 1066. Here see the literature values. Here we expect 930 for aluminum, 1300 for copper. And now at 10 gigapascal and at 20 gigapascal, you see this strong increase in the melting points. This is aluminum. Here, this is copper. And here are literature values, I think, from experiments, both for aluminum and copper. You see that this experimental increase is much more pronounced as what we observed here. So that's a point where the potential apparently was not too well suited. Yeah? And these high pressure properties, I mean 10 gigapascal is quite a bit, this indicates that the steeply raising part of the potential was not steep enough, I would guess. So that's again this question of transferability of potentials. These were EIM potentials. Later on, I think he also tried some other potentials, but not with much changes as far as I remember. Okay, so this is a high pressure melting point. So what one would conclude here, if you believe the temperatures, this should not lead to melting at these conditions, because the pressure is too high to allow for a melting. But again, I would say we're very far out of equilibrium, so you have extremely high density concentration, you have all these partial dislocations or stacking faults or so, which can lead to a lowering of the melting point or to a destruction of the lattice structure here. So, okay, so that's a summary of this study. The general trends are more or less well reproduced. So that's already nice. So this local, perhaps I should not call it melting, but local destruction of the crystal structure was observed. And the jetting was observed. But at somewhat higher collision velocities. I think that's mainly because of this mistake he made about the velocities. But then the simulation, three further shortcomings. The first is, if you look here, the thickness of this bars, I think it was 10 nanometer or so. In real experiment is a millimeter. And this means if you create a collision wave here, starting here, will be reflected back here on the free surface and then going back and forth. In a real material, this collision wave travels through the whole thick bar here and does not reach the interface, at least not as fast as it does here in the simulation. So that's one critical point.
Is there a way to put something at that surface to absorb these waves?
Right, that's what we discussed, but this was just a master thesis, so there was only limited time. So probably more important is that we assumed perfect single crystal without any defects. But on real materials, you always have an oxide layer. You always have some defects, grain boundaries, dislocations, and so on. And probably they also strongly influence the process. I think we tried it with different types of aluminum alloy, but I don't remember the results. So, and then the final point, which is also crucial, and there are some kind of artificial approaches to take into account this wrong heat conductivity, but basically it's just wrong. Heat conductivity in our system is far lower as it would be in a real metal. One could try to artificially increase the heat conductivity, but basically I don't know how to really model it. Yeah. Are you aware of any procedures which implement good heat conductivities? Okay, so this was this. Thanks again for your attention. This was just a small application of this type of simulations and experiments. Tomorrow I want to show another small set of application which I made myself a long time ago on irradiation damage or something which mimics irradiation damage. Okay. So are there any questions about this? Probably if you have questions I have to look up in the thesis, but and I think this explosion welding is also used just to form sheets, coated sheets. As I said.
Explosion welding.
Yeah, pardon?
Explosion.
Yeah. I think so. Yeah.
The application that I know of is superconducting wires.
Okay.
Because they are ceramics.
Yeah.
And forming them is difficult. And they are also
Okay.
processed using this kind of processes.
Mm-hmm. Yeah, I mean it's basically high velocity deformation. And on high velocity deformation, I mean, it's mostly people in green who are interested in that. At the moment, perhaps it's more acceptable. And I think it was discovered also that some, I don't know, some, what do you call it? So the balls from a cannon, that they adhered to tanks. Yeah.
Oh, I see.
This was just collision welding. Nowadays, I think they use, instead of lead in the past, they used uranium because it then also burns itself through the
And there are even pistols which carry this kind of bullets.
bullet.
Which are much more penetrating.
Right. Yeah. Bullet was a term I did not find.
GP zone you have mentioned here, like
Yeah.
from structure wise we can differentiate between them or something extra.
Yeah.
GP zone 1,
Mm-hmm.
2 and theta prime. So that is distinguished between them according to their structure only or something.
Right. Yeah. I mean, if you go back to the slide here, I think here it's best seen. I mean, these phases, they have all this characteristic structure of 1 copper layer, 3 aluminum layer, 1 copper layer. Yeah? While these here, they have a stoichiometry of aluminum to copper, and I think it's a copper-rich outer layer, and then there's a sequence of aluminum copper layers. What was it? 3 to 2, I mean, these phases, they have this interesting property that they are coherent here on the outer surface, so they nicely fit into the matrix lattice here. In this direction, yeah, if you take the proper number of layers, they again fit, I think, 7 of the aluminum to copper layers fit to 5 aluminum layers, or something like this, yeah. So
This is a dark field.
this is a high resolution dark field in the stem, so atomic resolution where you scan the sample with a very fine beam, electron beam, and you collect the angles scattered into large angles. It's called high angle angular dark field. So you have a detector which collects the electrons scattered into a certain range of angles. And the larger the angle, the more it becomes Z dependent. If you make a very small angle, you cannot distinguish light elements from heavy elements that well. But at large angles, you can very nicely distinguish copper from aluminum. Copper is bright, strong scattering. Aluminum is dark, weaker scattering. And I think, did I mention this? Another student of mine who did a number of these studies here, he tried to evaluate the brightness of each spot. I think I mentioned it yesterday, and to evaluate the, I think at least he claims that he is able to detect single copper atoms here. So the difference in brightness from a column which only contains aluminum to the brightness of a column which contains 1 copper, 2 copper, and so on. So for example, here you see a very bright spot. That's probably a point. Or here again. If you look for a while, you see many of these spots. These are all some copper atoms. I think you can even, I mean, that's for other samples, but you can trace the diffusion of gold on a surface. If you put little amount of gold on such a sample, you see them hopping in the microscope, which is not very realistic, I think, because you have the electron beam and the heating by the electron beam, but it's nice to show.
What would be the thickness of these samples?
This here, like 50 nanometers.
1.5 or 5.0?
Pardon?
1.5 or 5.0?
50, 5.0. Maybe a bit thinner. But it means, here you see the scale bar.
Yeah, this is about 10 nanometers.
It's 10 nanometers. So the extension of these, I mean, you can just count, yeah, it's so many 100 distances here. And this tells you, I think they are at most like 5 to 10 nanometers. So the probability that such a plate lies on a surface is not that high. Yeah. So you detect nearly all of them. But the strange thing, as I said, is really that you form completely different phases here as we observe. I mean, in normal, if you did the same experiment with aluminum copper, a similar concentration, and do the natural aging, you only see GP zones. Maybe I think I showed an example yesterday. Perhaps I can show. Yeah, this one is already sufficient. Here you see a normal one, yeah. So you once in a while here is perhaps a GP2 zone, but by far most of these precipitates are isolated GP1 zones. Here you see the metastable phase diagram with the GP zones and so on. So you see that there is at room temperature hardly any solubility And here's our nice electron microscope. This is how he proceeded to determine or to calibrate the contrast. He went across such a GP zone, registered the contrast. Here you see the aluminum lattice, and then here you see this increase in brightness. And since what he assumed is that this plate is circular, then from the width here, he can say so many are in this column. Of course, it's a rough approximation, but okay, and it's only 30 nanometer. Yeah, it's thickness determination by ELS, electron energy loss spectroscopy. So this way he could calibrate the method, and then he was able to index each of these points. That's another. And he determined the size distribution of these plates and so on. Maybe there's one slide I can show. I mean, here you see it for different aging times, 6 hours, 12 hours, 24 hours. That's quite tricky because this precipitation process takes place at room temperature. So you should not waste too much time during sample preparation and everything. Yeah? So either you cool your sample to much lower temperature, or you work very fast. Yeah? So that's, I think he now is quite good in this both. And here, this was what I wanted to show. This is this more or less arresting of this growth here. I mean, there are not so many data points here, but in the beginning, the average size increases very fast, but then it stops more or less. And I think there is a similar graph here for the average density. That's shown here. Initially, it's this density, and after a long time, 300 something hours, it does not increase very much. I mean, of course, they have grown a bit larger, but not considerably. So you more or less you can say that this process stops or continues very slowly. Here's a precipitated volume fraction. On the other side, some years ago, we had a request from a company in Augsburg from aerospace, and they had some aluminum copper alloys, aluminum copper lithium alloys. They stored for 10 years or so, and they wanted to know whether this would change the microstructure. At this time, we did not have this nice microscope, but I told them also it's much more costly to do electron microscopy than doing DSC. In DSC, you can trace, in calorimetry, you can trace the dissolution of precipitates. So we offered them to do that. And it turned out there's indeed a change in microstructure during these 10 years or so. Of course, it's not under controlled conditions. I don't know which temperature they reached in their material stocks there. So maybe were hot days with 40 degrees or so, but at least it was visible. Okay. But that's, just to add one last word, that's a nice thing nowadays. On the one hand, on the experimental side, we are really able to access the dimensions down to single atoms, and that's just the dimension where these types of model becomes important. Yeah? For the time scale, it's perhaps not that clear. I mean, still nanoseconds are very short. I mean, but for the microstructure, these nanometer or angstrom-sized processes, they can be well accessed. Okay. So for today, I have not more to present. I think we can stop here and finish a bit earlier. And then tomorrow, yeah, I can give one more presentation. You also have other things to present?
Planning tomorrow. So probably